Welcome back, everyone, to another explainer. Today, we're taking some pretty complex ideas and breaking them down into clear, actionable insights. Our focus? Inferential statistics. Now, I know what you might be thinking. Just a bunch of dry math equations, right? Well, actually, scratch that. I want you to think of this as your ultimate detective toolkit. You see, in the real world, we almost never have all the facts. Inferential statistics is quite literally the science of uncovering hidden truths from a very limited set of clues. Okay, let's take a quick look at our roadmap for today. We're going to cover 1. Population versus the sample, 2. Finding relationships in data, 3. The shape of data, 4. The central limit theorem, and 5. Testing your hypotheses. Let's jump right in. Starting off with section 1, population versus the sample. In a perfect world, if you were a detective, you'd just interview every single person on Earth to solve a case, right? In statistics, that entire massive group is what we call the population. But let's be real, we rarely have the time or the budget to survey an entire population. So instead, we rely on a sample. This is just a smaller, manageable subset of clues. But here's the catch. We have to be incredibly wary of sample bias. I mean, if our sample only represents a specific type of person, say we only interview the suspect's close friends, well, our whole investigation is contaminated from day one. Our subset absolutely must be a true reflection of the whole. So how do we actually do this? Well, this 5-step process right here is the exact methodology we use to go from a simple guess to a rock-solid statistically backed conclusion. First up, we define a hypothesis. That's our initial theory. Then we select our unbiased sample and we collect the data. Next, we run our statistical analysis, and finally, we interpret the results to see if our initial theory actually holds water. It's a rigorous, highly structured path to the truth. Moving right along to section 2, finding relationships in data. In our detective work, correlation is basically our way of seeing if two variables move together in some kind of predictable pattern. It tells us both the strength and the direction of that relationship. And the really brilliant thing about Pearson's correlation coefficient is that it sits on a super clean standardized scale. It goes right from -1 to +1, with 0 meaning there is absolutely no linear relationship whatsoever. Let's train your eye to spot these trends visually. On the left side, we're looking at a fairly strong positive relationship, a correlation of +0.8. Notice how as the x-axis increases, the y-axis reliably goes right up with it. Then on the right, we have a fairly strong negative relationship at -0.8. In this case, as one variable goes up, the other predictably drops. It's like clockwork. Now, if you remember only one thing from this entire explainer, let it be this absolute golden rule of statistics. Correlation does not imply causation. Seriously, just because two clues show up together at a crime scene in a predictable pattern, that absolutely does not mean one caused the other. Think about it. Ice cream sales and shark attacks both spike in July. But eating a scoop of vanilla doesn't cause a shark attack. They're just both reacting to a hidden third variable, which is the hot summer weather. Let's put some real numbers to this and look at another way to measure how variables move together. This is called covariance. Using some real data from our source material, like this specific height and weight data here, we can see the mean height is roughly 175.6 and the mean weight is about 170.6. When we calculate how these variables vary together, we get a covariance of 260.26. It's a positive number, so that simply tells us that taller people tend to be heavier. But there is a huge, glaring problem with raw covariance. The numbers can stretch anywhere from -infinity to +infinity. So what does 260.26 actually mean in the grand scheme of things? Is that a strong connection or a really weak one? Because the scale is totally unbounded, figuring out the true strength of the association is incredibly difficult. And that is exactly why we usually rely on standardized tools like that correlation coefficient we just talked about, which forces the answer onto that nice, neat -1 to +1 scale. Which brings us to section 3, the shape of data. Take a look at this. This is the famous normal distribution. It's just a beautifully symmetrical bell curve where most of your observations cluster predictably right around the center peak, which is our mean. The empirical rule shown here is an incredibly powerful shortcut for us. It tells us that roughly 68% of our data falls within one standard deviation of the mean, 95% within 2, and a massive 99.7% within 3. But what if we're trying to compare clues that are measured in completely different units? Apples and oranges, right? Well, that is where standardization comes in. By converting our raw data into what we call z-scores, we create a standard normal distribution. This is a very special curve where the mean is exactly 0 and the standard deviation is exactly 1. It creates a universal scale, which lets us effortlessly compare entirely different sets of clues against one another. It's brilliant. All right, section 4, the central limit theorem. Let's see how all this builds our foundation for actual testing. I want you to imagine a thought experiment. Imagine taking not just one single sample, but dozens and dozens of random samples from our population and calculating the average for every single one of them. If we plot all those sample averages on a graph, we build what is known as a sampling distribution of the mean. And here is where we hit a fascinating breakthrough, the central limit theorem. This theorem states that if your sample size is large enough, the distribution of all those sample averages will always approximate a beautiful, predictable normal distribution. And get this, that happens even if the original population data was heavily skewed or just a complete chaotic mess. It's basically statistical magic, and it's the absolute bedrock that allows us to make confident predictions. Finally, we've arrived at section 5, testing your hypotheses. Because we can practically never be 100% certain in our detective work, since, remember, we're only looking at a sample, not the entire population, we don't just give a single guessed number. Instead, we use a confidence interval. Think of it kind of like drawing a geographical perimeter around the area where a suspect might be hiding. It provides a highly probable range of values where the true answer for the entire population actually lies. It's our way of mathematically quantifying our own uncertainty. Let's take everything we've learned and apply it to a real business problem from our source data. Imagine a company rolls out an update to its customer service phone system, their IVR. Historically, the population mean wait time was exactly 100 seconds, with a standard deviation of 20 seconds. Management pulls a sample of 100 calls after the big update and finds the new sample mean is 95 seconds. Look at that. Wait times went down. Great job, right? Well, did they really? As we close out this explainer, I'm going to leave you with this final mystery to ponder. Is that 5-second drop statistically significant proof that the new system is a sweeping success for the entire population? Or is a 95-second average perfectly normal to see by random chance when you're just sampling 100 calls from a system that still actually averages 100 seconds overall? Knowing what you now know about sample sizes, normal distributions, and variance, how would you rule on this case? Would you calculate the z-score to finally uncover the truth? Think about it. Thanks for learning with me today, and as always, keep questioning the data.